Man hört das über Discord ja auch.
Very well. So our second lecture will be about random number generation. So we look at the concept of random sampling. On the first hand, we have the independence as a quality we want of random numbers. On the other hand, we have the identical distribution of these numbers. So these two parts make up random numbers in a random sample of a probability distribution. Therefore, we will now look at concepts how to produce such random numbers or how to obtain them for our statistical simulations. Well, the most obvious thing to do is to use some kind of physical process for creating random numbers. Such a process can be flipping a coin, rolling a dice. We know this from roulette, from lotto, from any kind of gambling. Also, there's decaying rates of some radioactive source or noise in the atmosphere, which might be the source of random numbers with a physical origin. The disadvantages of using some kind of physical process for random number generation are quite obviously it's really expensive to do it, not very easy to reproduce it, and we cannot always be sure with any kind of process that the numbers we obtain are really random and IID, independent and identically distributed. So tossing a coin might damage the coin if you do this 10,000, 100,000 of time and drop it several times in between. Or from the more physics world, Heisenberg's uncertainty principle states that you cannot actually observe the flight of a particle without interacting with it, having an impact and changing some of its effects. So hitting some detector with gamma rays actually influences the magnetic field in some way, and also the change and range of particles. So these physical processes are nice, but not what we will be using for statistical simulation, and also not in the real machine learning context of simulations. However, there are other fields like cryptography or obviously slot machines, roulettes, which still require these physical processes as the basis for their random numbers. So how do we get real random numbers in R? Random numbers from physical processes? Well, there is the random.org page, which collects such random numbers from atmospheric noise and allows you, based on the library random, to obtain random numbers out of their collective source and use them for whatever kind of simulations you would like to use them for. To give you an impression, this should look like this. This is what is meant by independent. Independent means that when I take the first to the 999th observations, the second to 1,000 observations should in any way not rely on what I was observing before. If this is not the case, I have a Markov process a kind of time series process where I have dependence based on my previous observation. So this is kind of the opposite of independent. Typically, this happens when we look at financial markets. The value of a stock tomorrow is highly dependent on the value of a stock today. This is not what we want with real random numbers. So sampling stuff like that in R can happen in two ways. The simple and easy thing to do is using the sample method, which samples from any kind of finite population. So basically, we state the size, the number of possible categories we would like to observe, and then we state whether we want to replace the values we've already seen or not. When tossing a coin and not replacing, I could not have more than two observations, because once I used up the 0, I can only observe the 1 anymore. Once I used up the 1, I can only observe the 0 anymore. Whereas replacing the values allows me to reobserve the same value several times. The opposite of that is sampling without replacement, as we do in the lottery each week, where once a number has been drawn, it will not be drawn again. Also, this sample methods allows us to create permutations as soon as you just provide it with a basic vector of observations or categories. You will get more or less random reordering of these things with the same length as the actual input. And also there is the chance to sample from the multinomial distribution, which means we generate draws from different categories, but not each of them is equally likely to be observed, but we provide each category with a different probability of observing it, which we can see here. The actual underlying probabilities of observing these categories from 1 to 4, the actual samples we obtain, and the actual relative frequencies. So this is the simple way of doing this for categories, but we are talking about much cooler random numbers of any kind based on any type of underlying distribution. So these are used in the context of statistics very often, and they are typically named pseudo-random number generators, because the numbers we generate there, they're not really random in the sense of the atmospheric noise of the physical process, but they are created in such a way that they appear to be random when we fill them in some kind of statistical test. So what we really need for these pseudo-random number generators is that when we initialize with the same value, the initializing value, which we typically call the seed, we want to end up with the same sequence in order to make our research reproducible. Therefore, obviously, this cannot be the same kind of thing as is happening with atmospheric noise. So it should be close enough to full statistical goodness of fit tests, to actual random numbers, but it should still provide us with this ability to be reproducible. Basically, we do not need this for every type of distribution, but we really mainly need to generate uniform random numbers because as soon as we do have uniform random numbers, we can derive any other probability distribution based on these. Why is this so special and so important? The uniform distribution is related to the quantiles and to the probabilities, which are typically numbers between 0 and 1. Now we do remember the cumulative distribution function as being the integral of the density function, and basically stating the probability of some value to be observed below a specified value. Probability of observing a value below 160 is somewhere around 18% in this example here. The inverse of this cumulative distribution function is named the quantile function, because we provide this function, the actual quantile, the probability which we would like to have up until 20, 40, however many percent, and I'm going in the opposite direction and reading which is the value, the smallest possible one, the infimum of all these, to fulfill this property. So basically there is the probability integral transform, which is based on this relation. So as soon as we get any kind of uniform random variable, we can always transform this uniform random variable with the quantile function, the inverse of the cumulative distribution function, and obtain the actual distribution function, f. This is the basis for the inversion method. So as soon as we can compute the quantile function, all we need to do is generate uniform random numbers and then transform them with our quantile function to any kind of probability distribution. So this is the main reason why we do not really need a specific pseudo-random number generator for any type of distribution, but it's good enough to have something which creates us uniform random numbers between 0 and 1. Main problem: in order to do this, we need to be able to invert the cumulative distribution function. Some of us might remember that this is not possible for every distribution function, but let's worry about the details someone later. So how to get at least uniform random numbers, pseudo-random numbers, in some way? There are several types of algorithms. We will talk about congruential random number generators, in particular about the linear congruential random number generator. This one is based on this recursive formula. So we end up with the next pseudo-random number based on our previous pseudo-random number with this linear transform multiplying by a and adding some c and doing the modulo division by m. So this modulus m should be a large integer. And when I'm saying large, I'm talking about really large, high powers of 10. Also, the multiplier a should be typically close to the square root of this modulus. And then there is the increment, which is somewhere between 0 and m. Based on any kind of starting value or seed, we obtain the next observation in the sequence as A times our seed plus C modulo divided by M. Now this is some really large number. In order to obtain something which is between 0 and 1, we divide this number by M. Due to the modulus here, there is no chance of this actually being larger than M, and we guarantee that it is between 0 and 1. Again, we repeat the same step for the second, third, and so on. So we obtain a sequence of uniform pseudo-random numbers in this way. This is a visualization of what this algorithm does. So in any step, we have the increment, we have the multiplier A to add, we have the increment, which is not obvious here, but which is added again. And then there's the modulus division. As we can see here, one of our main problems with this kind of algorithm is that we might up with a kind of cycle due to this modulus division, and therefore sooner or later this has its limits, and the smaller m, the sooner you reach this limit. This is why I was stating that this m, the modulus, has to be a really large number in order to allow us to obtain a reasonably large sequence of pseudo-random numbers. You will try out several values for this m, this a, and this c in a small and reasonable range in order to be able to see how this cyclic behavior might actually come to close in this algorithm and what this can have as an effect on the numbers we are generating here. In order to make this a little bit easier for you, this is the implementation of the algorithm, which you are very welcome to use for your homework exercises and which you should also use for exploring what's happening for different values here. Compare the numbers you obtain there with random numbers from the actual R function, R unif, and look at the quantile plots to see the difference in behavior of the pseudo-random numbers you are generating. Good. So now we saw how we obtain uniform random numbers. Let's talk about transformations now. So we want to have a good impression of what kind of target distributions would be available, what kind of distributions we might wish to end up with, starting from our uniform random numbers. So the simplest, the most famous of all distributions is always the normal distribution. Its parameters are the mean and the variance of the distribution, and it has this density function quite famously. Related in some way to the normal distribution is the student's t-distribution. Its parameter are the degrees of freedom of this distribution, which is basically some kind of scaling parameter for the x squared here, but which also adds up in this gamma function and in the power. For this degrees of freedom parameter being equal to 1, this is called the Cauchy distribution, and the generalized Cauchy distribution is this most heavy-tailed version of a t-distribution with a scaling parameter gamma added here to the x squared. Then we have the beta distribution. Beta distribution has two scaling parameters, alpha and beta, and those two basically affect the shape of this distribution. Most notably, the beta distribution is always between 0 and 1. Therefore, it is the most reasonable distribution for values which we can interpret as proportions, frequencies, or probabilities. So the normal distribution, the Gaussian distribution, the student's T, which is heavier tailed than the normal distribution, Cauchy distribution, which is also quite heavy tailed, but depending on the scaling parameter, tails can get even heavier than the base version. Then, apart from these possibly symmetric distributions, let's talk about some others. The first one is the gamma distribution, which is also the supercategory of exponential and chi-squared distributions. So the gamma has the shape parameter, which is the alpha, and the scaling parameter, which is the beta here. Its special case is the exponential distribution, which has the property of having this exponential decay and being memoryless in the sense of in whichever place I start, it will always have the same kind of degradation due to this exponential behavior. And then there's the chi-square distribution, which is also a special kind of gamma distribution and related to the normal distribution as being the sum of squared standard normal variables. In addition, there's also Pareto distributions, which are used in any kind of processes where we are interested in the tails, such as fraud detection or any kind of insurance. So gamma distribution, we're only in the positive range of values, as we are with the exponential distribution, which has this decay effect, with the chi-squared, which has behavior close to the gamma, and the Pareto, which starts from a peak and has this degradation behavior. A quick visualization of the relations between the different types of distributions. Don't worry, you won't need all of them, but it's quite useful to keep them in mind. Some of them are really frequently used in statistics and also for transformations, and all those which we will not use now immediately. Several of them we will revisit as soon as we start to look at Bayesian inference. So normally distributed variable, as soon as I look at e to the power of x, I end up with a log normal distributed variable, which means if I would apply the logarithm to this thing, I would end up with a normal distribution. As I said before, the sum of standard normal distributed values squared is chi-squared. The exponential distribution basically is a gamma distribution where the alpha parameter is equal to 1. The chi-square distribution is a gamma distribution where the alpha is equal to k half and beta is equal to 1/2. Also, there is a relation which is less obvious, which is between the gamma and the beta distribution. So when I sum up two gamma distributed random variables and I divide the first one by this sum, I calculate the proportion of the first one of the sum. I end up with a beta distributed variable where alpha is the first of the two shape parameters and this beta is the second of the two shape parameters. So when I take a normally distributed variable and I divide by the square root of some chi-square distributed variable, I end up with a t-distributed variable. This relation we will revisit definitely when we look at the Bayesian statistics examples. Also, this is one of the most frequently used relations between distributions. Starting from two chi-square distributions, looking at their ratio, we end up with an F distribution. And this specific type of ratio where I divide each of the random variables by their degrees of freedom, and then I take the ratio of those two, is the basis for the F-test and its most famous application, the ANOVA, the analysis of variance. Also, I can relate the exponential distribution to the Pareto distribution in such a way that taking e to the power of x from an actual exponential variable, multiplying by some base y0, I end up with a Pareto distribution with this y0 as its parameter. So you can obtain all of these directly from R, either from the base package or from some additional libraries. In case you're not yet aware of it, they are all encoded in the same way. There's D for density, P for probability cumulative distribution function, Q for quantile function, and R for random numbers of the specific distribution. And instead of this foo, you just add the shortcut for the specific distribution you would wish to simulate from. So now that we had some impression of what kind of transformations would be available for us, what kind of pseudo-random numbers we could generate based on our uniform random numbers, let's look at other ways of how to do this rather than just inverting the cumulative distribution function. So what else can we do? There is a method which is much more generally applicable, which is called acceptance rejection method. So acceptance rejection method is based on the following theorem. Let f and g be two density functions where there exists a constant c such that f of x is less or equal than c times g of x for all x. Then let y have a density g and let u given y have a uniform distribution on 0 to c times g of y. Then x equal to y given u is less than f of y, has the density f. Let's talk about what this actually means as the basis for an algorithm. So the density f, which we wish to obtain is the target density. However, we cannot really sample from this density F directly, or we cannot even obtain it by transformation, but we can at least generate random numbers from a so-called instrumental density or proposal density. And we know that G is greater or equal than F, at least when we multiply it with some constant C, which is greater than 1. So then the acceptance rejection algorithm has the following steps. First, we generate a random number from our instrumental density G, and in addition, a uniform random number U. We accept this proposed random number from our instrumental density if U is less or equal than f of x divided by c times g of x. If U is greater than this value, we will reject the proposed value and start with a new proposal. So visualized, this means that we have our instrumental density, which is greater or equal than f in all cases. We have this very unusual density for f, from which we cannot sample directly and which we can also not obtain samples from with the integral transform. But we can sample from G, and then we will accept this value if the additional uniform variable we created is in the blue range, or we will reject it if it is in the red range. So you can see the larger the distance between this instrumental variable and the target variable, the less likely you will accept these values, and the more likely you will reject them. In places where they are close together, you will reject very, very rarely and accept very often. So we will get a good algorithm depending on how large this constant is and how far these two distributions are apart. So the constant C has to be larger than 1. Having a probability density function means that the integral of this function has to be equal to 1. So basically, any f and g have to have the same total integral from minus infinity to plus infinity. In order for g to be greater or equal than f in all places, for all numbers, I have to multiply it definitely with a number which is greater than 1. Otherwise, I will not obtain anything which has a larger area under the curve. Therefore, the probability of accepting any type of proposal is 1 divided by this constant C. So the larger the constant I require, the more I have to blow up this proposal density, G, in order to have something which is always above the F, the harder it will be for me to actually accept my proposal values. This is a problem because the performance of the algorithm depends on it. So in order to obtain n samples from F, I have to sample C times n random numbers from G and from the uniform distribution. So as soon as C gets really large, I need a really large number of other random variables to obtain the random variable samples from the target distribution I'm looking for. This method, however, has the advantage that we do not really need the normalizing constant of any type of density f in order to be able to sample from the density anyways, because this is only up to some numerical constant anyways. Therefore, it is often used in Bayesian statistics, and we will also revisit this acceptance rejection sampling in the context of Bayesian statistics under the name of Metropolis-Hastings sampling. So let's look at a specific example, how to generate random variables from the normal distribution. We will first look at how to approximate the inverse CDF. As we remember, we cannot even integrate the density function. We do not have a closed form cumulative distribution function for the normal distribution. Therefore, we also do not have a closed form for the inverse of the cumulative distribution function. We will then look at acceptance rejection sampling and also at one type of a transformation method which is specific for the normal distribution called the Box-Mahler algorithm. And we'll talk about this one because it's the most generally used algorithm for generating normally distributed random numbers. So first let's start with the inverse method to generate normal random variables. The CDF of the normal distribution, as we remember, we cannot solve it explicitly. However, we have the chance of getting some kind of approximation which is related to the Taylor polynomial of the exponential function. With these specific values, we obtain something close enough to phi of x. Similarly, we can get an approximation of the inverse of the cumulative distribution function by this rational function with these values. These two approximations are exact up to an error of 10 to the power of -8. So basically, those two work well in the center of the normal distribution. They will not work so well in the tails of the normal distribution as soon as our value gets somewhat close to the approximation error. So based on this, we get an algorithm for simulating random normal distributed values. And as we can see, this works well in the center. However, we start having problems in the tail. In this tail, this one is not heavy enough, it's too light. For this specific case, the upper one is more or less okay. Let's now look at acceptance rejection method for normal random variables. So a distribution which is definitely above the normal distribution as soon as we multiply with some constant is the Cauchy distribution. The main reason for this is that the Cauchy distribution has heavier tails than the normal distribution. Therefore, we only have to use this scaling factor C of 1.6 in order to blow it up a little bit in the center, whereas out there in the tails, we have the guarantee that up to plus or minus infinity, those tails will always be above the normal distribution tails. So we simulate from the Cauchy distribution, which we do here. We simulate a normal uniform random number, and we accept based on this comparison of the uniform random number with this ratio of our target distribution compared to our Cauchy random variable. As we can see here, this simulation inherits the property of the Cauchy distribution it was sampled from. The tails of this distribution are slightly too heavy for real random numbers. In the center, everything's fine, but the tails are too heavy, in particular here at the bottom. So the last thing to look at is the Box-Muller algorithm. This method is specific for normally distributed variables, and the relation, as we said before, when we take the sum of two normally distributed values, they are chi-squared distributed with 2 degrees of freedom. This is the polar coordinate form of writing x and y coordinates in the two-dimensional space, rewriting it as the radius and the angle, where the angle is actually uniform between 2, pi and 0. So based on this, we transform these randomly generated polar coordinates in order to obtain normally distributed x and y coordinates. So we obtain two separate independent normally distributed samples out of this algorithm. As we can see here, this one is by far the best one of all the simulations we did. The tails are working fairly well in the first one and super well in the second one. And that is also the reason why this Box-Muller algorithm is specifically used for generating random, pseudo-random numbers from the normal distribution. Good. That would be our lecture for today. You will go through all this through 3 examples in your exercises where you summarize the pseudo-random number generation with linear congruential random number generator. You will look at the exponential distribution and how to use the transformation method there. And you will also look at the beta distribution and how to apply acceptance rejection sampling for this distribution. Good. So this is more or less it. Have fun with your exercises and have a nice day.